years. That's 15 years.
Oh, you graduated in 2003.
So I think we're live on YouTube right now.
I have to say I'm really impressed with that technology.
It's really easy.
Be
It's
first.
amazing.
Yeah.
So you'll turn that off when we switch to the private thing, right?
Yes.
Just making sure.
No. It's gotta be there for posterity.
Well,
You're gonna say all that stuff that you don't want to be publicized elsewhere, right? Amazing.
what do y'all think we should say? Oh, no. If I had shoe glue, I'd offer it.
I was actually leaving class this morning and noticed that I was missing part of my shoe. I went back to class to find it because it was gonna fall down. I was gonna fall down. Is somebody watching? Hey, you are watching. Our second.
I know.
Second committee member. Congratulations. Hi.
Oh, phew. Oh, yeah. Nice to meet you. Hey, so you got my message, right?
Yeah, so I was thinking, like, where we're doing this, if we're gonna be continuing this afternoon. Thank you. I was gonna let Kane know, but I think we're fine.
No, that's good. I'll be committed to that.
Perfect, perfect. I think he was worried, so.
Well, we should also the other guy.
Yeah, but if we're having a pick.
Let's do it. Let's do this up one.
I would talk to him. I'm much better well, I leave next Thursday for Europe, just for a few days.
Oh.
And
I was
then,
like, she got already?
I'll be back on the following Monday.
Okay.
But early next week I can do it.
Next week? I was going to Monday, Tuesday.
Monday afternoon I can do.
Let me tell you a few things.
Tuesday.
Maybe.
What do you think about you? Are you anything with that?
Sharon, you're early.
Yeah.
Did you tell Sharon I was a 2?
No, you know, I'm CEO of Guardian Health now.
You're what?
I'm the CEO of Guardian Health.
So now you have to show up to things on time?
I
Is that
actually have
like
to
the
show up
rule?
on time. When you're a CEO, you can't afford to be late,
Okay.
apparently. I thought,
This is
I
the
think that was-
startup for the kiddos we're doing. What's the premise?
oh, predictive cost.
Yeah, so there were some kids that were talking. Who were they? Who were the students from UT, right?
Mhm.
Who were the students involved?
Joyce and Yuban.
Those were Jadip students.
Joyce is actually joined with me, but yeah.
Okay, sorry, I didn't mean to give
No,
you
no,
the
no,
yeah. But it's with Joydeep.
Yeah. But Kate.
Kate is working for them.
Yeah.
That's what it is.
Oh,
Fantastic.
I like Kate.
No, you can't like her that much. She needs to come back.
She and I just finished the meeting, and she had over-prepared as usual. And
She needs to be on leave from the PhD program just through December.
I
So
see.
you need to work with her on that.
Okay. But when she got done, I was like, yeah.
No, but seriously, I think she really does want to come back. So I think
Maybe you shouldn't go to Italy
it's not
then.
her thing.
How many of you?
Everybody.
Everybody?
I've enticed the PhD student. I told them to come visit if they're doing something cool. So that's what I have to.
Only if you're doing something.
Either way, there.
But I'm telling you, the guy who develops all the apps, he's maybe 19, 20. He's really good.
Really?
Yeah, he's better than any of the
Is he a
others.
student or is he just?
Yeah, he's a sophomore.
Hey, Stubborn. You want a copy of the stuff here?
Okay. Maybe I should say that
Not very official.
I'm not late.
You're not late. We still
You
have
gave me this look.
10 seconds left.
No.
We're still missing
I
two.
think,
So.
I
Yeah.
think it might be that I arrived before.
Actually,
Never
Is
happened.
it?
Yeah. You're right.
Sharon was early.
You're right, that's what I found disturbing.
So which time zone are you in?
EBJ.
Right room. There's plenty to eat and drink if you want anything. There's coffee and tea if you want. That one I believe is hot water.
Just warm hot water.
And then that's coffee.
So what happened with those, the coffee and tea? They're not delivered or?
I decided I was just going to bring my own tea.
Oh,
I didn't know they offered us. And I
So
opted
the
for
water is
Starbucks
from us?
coffee. Yeah, the water's from us. But I opted for Starbucks coffee instead.
those are not.
Oh, am I the last one or something?
No, we didn't.
We're both on
I guess I
time.
can circulate this if you.
Strange
I'll just
feeling.
keep it with the whole
Okay.
The Shriram is here ahead of us.
So this thing is being broadcast on YouTube?
Yeah, it's live right now, actually. So it's just broadcasting the slide deck
Okay, I just want to
and then
And
the audio as
too.
well. Correct, yeah.
Wait, but not us.
Oh, thank you.
Not video, but audio.
Oh,
hi.
But he'll turn it off.
Oh.
He literally switch, for sure.
okay, I just praise Kate on YouTube.
Anybody sitting here?
PJ, so you can hear. You just did what?
Can I grab you a water or anything while I'm over here?
Yes, please.
Sure.
Very good.
Go ahead.
It's a good morning, it's like you forget about it.
Well, he is tall, so I'm gonna sit over here.
No, don't do that. We can switch.
No, that's okay. That's fine.
Please.
No, it's good, it's good, it's good.
You sure?
Yeah, I'm fine.
Thomas is going.
I just want to. I can block Christine.
Huh? No, I'm fine, I'm fine. Thank you.
I think we have everyone, so
Go for it.
go ahead and get started.
So ECs looked very punctual. And I
So
thought I was
happens, yes.
right on the dot, 2:30, and I'm the last one.
Okay.
There you go.
I'm gonna go ahead and get started.
Should roll the floor.
And you guys feel free to meander and grab food while I'm talking. It's all okay. So good afternoon, everyone, and thank you everyone for coming. And thank you also to the people that are tuning in remotely on YouTube. Welcome to my PhD defense. I'm Jonas, as I hope you know. And this talk is all about two complementary themes, finding and sharing digital information in a kind of emerging computing environment I like to refer to as pervasive computing spaces, which are physical spaces that are very digitally accessible because they're densely populated with wireless devices that humans can use to interact directly with their environment. So all of the sensing and computation and communication that happens directly within these spaces produces huge amounts of spatiotemporal data, information that is somehow about the place and time in which it is generated. So applications that target these kind of environments have very hyper-localized information needs. They need support for accessing the living, breathing landscape of data that is in users' immediate surroundings. In particular, applications need support for, on the one hand, sharing data, so generating data and moving it over network connections. And on the other hand, they need support for searching data, so finding information distributed across many devices relevant to a user's query. Applications also need support for reasoning about data, because as we'll see, this kind of information is very contextual, very situational. It can mean different things in different places and times. So if there's one thing that's for sure, it's that Austin has a lot of festivals, right? So one that happens every year is Austin City Limits Music Festival. And for 2 weekends, about 75,000 people jam themselves into Zilker Park and go to shows and eat food. It's just a big party. It's a lot of fun. So at the festival, attendees have very hyper-localized needs. They need to know things about right here and right now. So for example, if I'm at the festival, I may want to be alerted when my friends are nearby, or find pictures or videos of a particular show from the front stage, because I'm way far in the back, not VIP. Vendors also might want to have an application that can help them deliver advertisements to particular users. So for example, if I'm a beverage vendor, I might want to deliver a coupon to people that have recently purchased salty snacks. So I was actually at the last Austin City Limits Music Festival, and I was actually right about here in the crowd. And I remember I had a friend who was in the crowd too, and we were trying to coordinate via text message, find a place to meet up, see some shows, eat some food. But my cellular network was so jam-packed with people that our text messages were taking upwards of 30 minutes to be delivered, sometimes not even at all. So this is kind of an extreme example, but it does demonstrate the fact that in these kinds of environments, device-to-device interactions can sometimes be more advantageous than going to the cloud. So for certain applications, for example, the round-trip time to the cloud could be too slow. Think latency-sensitive applications like augmented reality. And in some environments, short-range wireless protocols like Wi-Fi and Bluetooth may be more efficient than long-range wireless protocols like cellular. Probably what happened in my story was that my network was so crowded that infrastructure resources were scarce. So motivated up by these practicalities, my dissertation focuses on challenges in device-to-device interactions. So let me drive this home, and then we'll jump into the meat, into the good stuff. So the opportunity here is that emerging computing environments generate huge amounts of spatiotemporal data that can be exploited by co-located users and applications. However, there's little general purpose support for finding, using, and sharing this kind of data in a device-to-device fashion. So my dissertation addresses key formal and practical challenges in supporting these fundamental application needs. And the rest of the talk is going to be divided into 3 high-level conceptual blocks. And the first lays some formal groundwork and introduces models of metadata that annotate data with spatiotemporal meanings. So building on those foundations, the next piece introduces constructs with the overarching theme of making the developer's life easier, simplifying the development of applications for these environments. And the third and final piece aims to provide the system support necessary to deploy our approaches in real-world environments, real-world devices. So I'll touch on pieces of each of these and hopefully not put you all to sleep. Let me dive into this first piece here, and I'm going to begin by talking about 2 variants of a formal model for metadata that enriches data with spatiotemporal annotations that can simplify the specification of application behavior and then also enable complex reasoning about data itself. So, as I've said before, data in these kinds of environments is very spatiotemporal. It's very situational. So in different places and times, it can mean different things. For example, at the festival, a sensor reading that says the ambient noise level is 110 decibels. At the festival, that could be relatively quiet. In someone's home, though, that could be screaming loud and mean that either something's terribly wrong or there's a party there and we all need to be there right now. Second of all, data is very transient. It represents the changing state of a real-world environment. And finally, data itself is mobile because the devices that generate and carry it are themselves mobile, but also because data can be moved between devices across network connections. So we believe there is huge inferential power in accessing this contextual history of data as it lives and moves. So we introduce a formal model of historical metadata that captures the contextual history of data as it moves through space and time. So associating historical information with data is often referred to as data provenance and has received attention in distributed file systems and large-scale data stores. And in those applications, the metadata tract is the logical history of data objects, things like file edits and history of ownership. So our approach is similar in spirit, but aims to capture the physical history of data as it moves through space and time. And in an entirely different domain, pervasive computing, there is a huge spectrum of approaches that all try to query and access data in a very efficient way. However, none of them explicitly capture the contextual history of data itself to make additional decisions and distribute more information. So we introduce a formal model of spatiotemporal data provenance, and it comes in two flavors. The first uses an explicit coordinate system, a coordinate-based form of space, and the second is a more general purpose extension and uses a more implicit causality-based form of space. So I'm going to describe our model through the lens of the first variant, and then I'll differentiate it from the second one. So our model begins with a phenomenon, which is anything that happens in the real world that can be associated with a place and a time, a sensor reading, the location of a moving object. When that phenomenon is sensed, an observation occurs, which generates a piece of digital data that captures some quantum of knowledge about the physical phenomenon. The foundation of our metadata model is a data structure called a spatiotemporal trajectory, which captures first the actual dynamics that that piece of digital data undergoes, and can also be used to evaluate the relationship between digital data and the phenomena it represents. So within our explicit model, a spatiotemporal trajectory is a set of vectors within an explicit coordinate system. Let me tell you what I'm talking about. So imagine there's some device that's able to sense the concentration of some chemical in the air. And at a particular place and time, it takes a sensor reading and generates a piece of data. And as this data moves, as either because of the device moving or the data is shared with other devices, its spatiotemporal trajectory captures the movement of that data through the coordinate system. But the phenomenon can also undergo dynamics. Perhaps there's some wind that is changing the concentration of this chemical in the air. Provided an initial relationship between the datum and phenomena, so the direction and speed of the wind, our spatiotemporal trajectories can be used as input to computations that enable reasoning about the relationship between these two elements as they both undergo dynamics. So for example, the validity of data may decay in space and time, as for example, data gets older or moves away from the place that it was generated. So we can compute different forms of decay directly on top of these spatiotemporal trajectories. Trajectories about the same phenomena can reinforce one another when their datums meet each other in the field. So for example, the trajectory of an older piece of data can be corrected by the trajectory of a newer piece of data. We can also smooth trajectories to reduce their resolution. And given we have a bunch of data about the same place, we can aggregate observations along a combination of trajectories. So for example, in a smart city, we could sum the number of available parking spaces along the route of a vehicle as it travels.
So the trajectories are continuous or they can be broken? So I go switch off my phone, then it starts somewhere else. So now you don't know whether...
Right, so we don't make any assumptions about that in the model. It's just, as long as we're tracking the movement of a piece of data, then its trajectory gets updated. But you're right, if we stop tracking, then we'd have a gap in the trajectory, which wouldn't be good. So those were a few examples of the practical use of our trajectories for reasoning about data. But we can also use our spatiotemporal metadata to simplify the specification of data-dependent behavior. And we can do this through very concise rules. So let me give you some examples. In pervasive computing applications, it's usually very important to know when and where to delete data. So maybe we would like to delete information when it has moved more than a certain distance away from a reference location. This rule captures that. Or we could write a rule that says, hey, I actually want to delete data after it has traveled more than some cumulative distance. Many pervasive computing applications also try to keep data where it is spatiotemporally relevant. And so we can capture this otherwise pretty complex behavior in this very concise rule. And the novelty here is that these rules themselves are spatiotemporal and only use our trajectories as input. So similar to how spatiotemporal data provenance, rather, is used traditionally, we can define administrative regions and use rules to or use our metadata to gauge how much to trust data, depending on where it's been and how old it is. You can also imagine that we could write rules to guide queries along gradients defined by the reverse trajectories of relevant information. All right, so defining our trajectories within an explicit coordinate system allows for some nice synergy with trajectory work that was developed for use in moving object databases. It also allows our metadata to be directly used in Cartesian-based applications, for example, geo-routing protocols. However, pervasive computing applications typically operate on resource-constrained devices that might not have the hardware or energy required to localize those devices within an explicit coordinate system. Moreover, the physical environment itself may preclude localization and use of particular positioning technologies. So for example, satellite-based position does not work well indoors, if at all. Motivated by these practical limitations, we next introduce an extension of our metadata model that uses a more implicit form of space that's more general purpose and can support a wider range of resolutions. So let me kind of contrast these two. So within our explicit model, a spatiotemporal trajectory is defined as a set of vectors within a coordinate space. Within our implicit model now, oh, we can't even see that. That's horrible. A spatiotemporal trajectory captures the causal device-to-device propagation of data as it moves between devices within time-varying network. So to formally define this variant of our model, we extend, or rather enhance, a formal framework called the time-varying graph formalism, TVG for short. So very much like a static graph, a TVG is defined by a set of vertices and edges where, in our case, a vertex represents a wireless device and an edge between two vertices represents one-hop network connectivity. Now we add on some extra temporal candy. A presence function indicates the intervals during which particular edges are active, and a latency function defines how long it takes for a message to traverse a single edge. So far that was the TVG framework as it was initially introduced. We enhance this framework with some data-dependent semantics and tack on an extra set M, which just contains triples containing, well, indicating what data was sent on which edges and at what times. And this may seem simple, but it's actually rather powerful. And I'll show you why. So within our model, we stipulate that each node maintains a local copy of a TVG. But this global view of the graph only exists virtually, not physically. So in reality, each node's local TVG contains, on the one hand, its first-hand knowledge of its own network interactions, and second-hand knowledge obtained from spatiotemporal trajectories attached to messages that it has received. So you can kind of start to see the inferential power of our extra data-dependent semantics, because I can view this graph in two ways. So I could view this in a data-dependent way concerning what data is about. Maybe I'm at the festival and I notice that, hey, data about the Pearl Jam concert shares similar spatiotemporal trajectories with data about beer purchases, which either means that Pearl Jam fans are heavy drinkers, likely, or that, well, the beer vendors are close to the Pearl Jam conference, or that'd be fun, Pearl Jam performance. But I can also ignore what data is about and just consider the topology of the graph and view it in a data agnostic fashion, which gives me a historical window into previous time-varying states of the network.
So I'm confused a little bit. So those vertices keep moving, is it? In physical space?
Correct.
So none of them is physically tied to some stationary point.
Correct. So I'm about to show you how we formally define our spatiotemporal trajectory. And you're right, it doesn't use any form of physical space. It's all relative. So again, in a virtual sense, a transmission network captures the complete causal spreading history of a piece of data as it moves through our time-varying network. And a spatiotemporal trajectory captures a portion of that transmission network. And what exactly goes into the trajectory is determined by an update strategy, which is essentially a policy or rule that transmitters use to update the trajectories of messages before they propagate them to a receiver. So it's very difficult to see, I apologize, but in the dissertation we provide a few sample update strategies that each provide different levels of coverage of the representative transmission network. So for example, our neighbors strategy provides good spatial coverage, but only at an instant in time. Whereas our journey strategy provides good temporal coverage, but only along a single causal path. So
in the previous
Yes.
diagram, the different edges at different times.
They do, yes,
Okay. So they don't necessarily all exist at the same time.
correct. So they're just shown kind of in a flattened way here so you can see the differences.
But each edge is annotated so you know that what time it was.
Exactly.
Okay.
And there may even be multiple intervals on an edge.
Okay.
So to help combine trajectories in meaningful ways, we provide spatiotemporal operators. And what's convenient is that because we represent trajectories as causally ordered sets, they very naturally lend themselves to the use of set operations. And also what's convenient is that we can restrict these operators to particular domains. So for example, we could just consider the spatial domain and consider the causal structure of messages propagation, which would produce a static graph. And then we can run traditional graph algorithms like click detection. Or I can consider the temporal domain and add in timing of events in our graph. So using this information, we could do things like analyze inter-contact patterns, which is how most mobile social network routing protocols operate. We can also add in our data-dependent semantics and consider what data is about. So for example, maybe I'm a vendor at the festival and I want to restrict my analysis to trajectories and data about snack purchases. So we can restrict our views on the graph to different domains. And in the next section, we'll see how we can use these operators to formulate higher level inferences. So let me wrap up this first section, and we'll move on to the second one. So we first introduced a formal model of spatiotemporal data provenance that uses a trajectory data type to capture the movement of data through space and time. Then we provided an extension of this model that uses a more general purpose implicit form of space. And both of these models can be used as input to rules that can simplify the specification of an application's data-dependent behavior.
You seem to imply that explicit is a special case of implicit, but that's not the case, really, right? I mean, the information that you have in explicit is not there in implicit. For example, physical coordinates.
Right.
So the kind of reasoning I could do with the explicit model, I cannot do reasoning with the implicit model.
That's true. They could
So you
target
need
different
both.
applications.
Of different applications.
Right.
Can you comment a little bit on the overhead, given that we're in a resource-constrained setting?
Absolutely, yeah. So in the dissertation, we do actually do some overhead analysis of the explicit model. And what we did was we varied the resolution that we update the trajectories, and also the dynamics of sensed data and the dynamics of moving objects that sense the data. And the results were pretty intuitive. I mean, as you increase your resolution and things become more dynamic, then overhead goes up.
So is it plausible that at some point using D2D with the overhead to track this information is not efficient, and we're better off trying to squeeze it through the cellular network?
Possibly, yeah. Or you could compress things, or you could generate an identifier that maps to a trajectory that might live in the cloud.
So that was going to be my question. So there seems to be a fair degree of redundancy in the way the thing was architected and the type of information
Right.
like that. You would think that temporal variation timescales matter a lot.
Absolutely.
Have you looked at how much you can compress this?
No, we didn't do any compression analysis. We stayed very high at the application layer.
For the implicit, the overhead depends on which of the update strategies you use, right? Like, is that
Precisely,
the
yeah.
reason why you wouldn't always just use Journey Plus? Because Journey Plus would look like the one you should always use.
Correct, yeah.
How would you choose, kind of to Gustavo's questions, like how would you choose which update strategy to use based on your overhead requirements or application needs, or you don't have a good sense of, do you know what I mean?
So yeah, each of the update strategies for the implicit model provide different amounts of coverage of space and time. So depending on the constraints of how much overhead you can incur in your application, you can pick whatever provides the best spatial and temporal coverage for your application's needs.
Is there any reason why at one hop, like if I'm passing a packet, and so I'm collecting the trajectory associated with that packet, one device could say, I'm using the Journey Plus update strategy and capture that, but then the next one would be like, no, we've surpassed some limit of overhead in this packet, and I could trim or not, or would that be disruptive to the update strategy? Or I can switch update strategies kind of mid.
It's feasible to do that. Yeah, you definitely could switch things or just throw away a trajectory and take away
Keep
the
the
subset of history that you want.
So I guess everything is done on a best effort basis. I mean, there's no notion of completeness or correctness.
Correct, yes.
I guess the cellular network would be seen as a backup method
Yeah.
if this fails.
Or Wi-Fi
Oh,
hotspot.
Does Austin City limit? Do they have Wi-Fi there? I'm just curious. No.
I don't think they have public Wi-Fi. There are vendors that set up hotspots that allow you to do run their application. But no, there's no publicly accessible Wi-Fi. That'd be really nice. Okay, well, I'll continue if there's no more questions. So the next section, the theme of the next section is making the developer's life easier, simplifying the development of applications that target these emerging pervasive computing spaces. And I'm first going to describe a middleware that we developed that enables developers to program their applications using the rules that we talked about in the first part of the talk. So a little bit of background first. Pervasive computing applications typically define a purpose-built data model, which is fine, but the focus of applications is usually querying and accessing that data in an efficient, distributed fashion. And the rest of the application's data-dependent behavior is scattered around the application. And the conditions that trigger that behavior are often implicit. So not easy to interpret and makes engineers uncomfortable. So we believe a more general purpose approach is to express that data-dependent behavior within rules that make those contextual dependencies explicit. So now I'm going to talk about a piece of middleware we developed. It's very extensible, that enables developers to, on the one hand, attach spatiotemporal metadata to their existing application data, and then also program their applications using rules that are driven by that metadata, if they want. And our rules provide some general purpose semantics for sharing and using data to get application-specific data out of these application silos. So it's no big secret that creating these kinds of distributed and disconnected applications is very, very challenging. And the whole idea of using rules to program applications is by no means new, and has even received some attention in pervasive computing. For example, the tuples on the air infrastructure. However, these approaches require the use of a specific data model. So our middleware is very general purpose and does not tie developers to any kind of data model, but our middleware sits on top of their existing application data as an independent layer. And on a related note, the publish-subscribe paradigm is kind of a mini rule-based paradigm in and of itself. I mean, you have two rules, publish, subscribe. However, contrary to what you might hear, publish-subscribe is not a silver bullet and is not a one-size-fits-all tool. So our middleware doesn't restrict developers to any particular mechanisms, but it could be used to implement publish-subscribe. Now, the core of our middleware is a graph-based data store with two independent partitions. And the first is used to store application data directly or store identifiers that map to application data in an external data store. And the second partition stores our spatiotemporal metadata, where each of these green chains represents a spatiotemporal trajectory that has been associated with particular application data. And rather than require developers generate and use data by hand, our middleware provides some abstractions that wraps this raw graph data in some abstract layers and provides extensible interfaces that enable a developer to write rules that once registered with our middleware will execute automatically. Let me show you what I'm talking about. In our middleware, a rule is an abstract class with hooks that enable developers to attach blocks of code to points in the rule that will be reactively called whenever the rule's conditions are satisfied. So for example, in the previous part of the talk, I gave the example of a rule that would delete a piece of data after it moved more than a certain distance away from a reference location. I'm going to do a big no-no here. I'm going to show you some code. So this is truly the extent of what I would have to write if I was a developer trying to implement this rule. I would first extend an abstract class called user location change rule, which has a single abstract method called onUserLocationChange, and you might guess it is called whenever the user's location is changed. Then that method, I just check if my distance is greater than this rule's threshold, and if it is, then I grab the data this rule has been associated with, and I delete it. My job as a developer is done. That was an example of a spatially parameterized rule, but our middleware also provides constructs for temporally parameterized rules, and even rules that can be parameterized by the state of data or metadata. It's all very mix and match, extensible. In the dissertation, we use this middleware to conduct a couple of case studies, but I want to focus on the second one here. And we used the middleware to demonstrate the utility of our implicit spatiotemporal annotations for improving the performance of ad hoc routing. So let me give you a little background, and then I'll describe this use case. So remember that a transmission network represents the complete causal spreading history of a piece of data as it moves through a time-varying graph. Now, the transmission network is only virtual. It's not practically accessible. So transmitters attach spatiotemporal trajectories, which are a subset of the complete transmission network. And the contents are determined by an update strategy. Receivers use this partial knowledge as, first of all, a view into the contextual history of particular data, but also as a window into previous time-varying states of the network. And because acquiring a complete view of a transmission network is impractical, it sure would be nice if we could use incomplete local knowledge to do useful things. So in the dissertation, we show how we can use incomplete knowledge to, first of all, estimate global network characteristics pretty accurately, and second of all, make inferences about remote nodes knowledge. So I walk up to you and I say, I think I know what you know. And I want to talk about this second one here because I think our results are pretty impressive. So let me give you the setup. The setup is we simulate an epidemic routing protocol on top of empirical data sets of human proximity. And the high-level approach is that given that messages propagated close in space and time will follow similar paths through the network, their trajectories can be stitched together to fill holes and supplement for incomplete contextual history. We give you a very simple example. Assume we have 4 nodes here, and at a particular time, node A transmits two messages through different causal paths: blue message, red message. And for the sake of the example, let's also assume that node A did transmit this message, the red message, to B, but because of some incompleteness in the network, maybe because of a routing protocol or because the network itself is kind of lossy, node B does not propagate that message to you. But node U can see that node A is in the intersection of these trajectories. So it knows there was at least a chance that node A propagated the message to node B. So given this incompleteness in the network is predictable, which we indicate with this p-sub propagation parameter, node U can compute its confidence that node A actually did transmit the red message to node B. Let me show you how we use this. We use this knowledge inference method to reduce the routing redundancy in our epidemic routing protocol. And the approach is that I run my epidemic routing protocol like normal, except before I transmit a message, I first perform knowledge inference on the receiver. And if my confidence that the receiver has already received a copy of that message is greater than some threshold, then I hold off. I don't transmit the message. You've already got it. I don't need to send it. So I'm going to show you two charts here. We first varied our piece of propagation, the probability with which messages are propagated, and we fixed our confidence threshold at 1/2. And what this chart shows is the tall dark gray bars are the redundancy rate achieved by our unassisted epidemic routing protocol, and it's typically between 35 and 50% of messages that were wasted bandwidth. The rest of these bars show the redundancy rate achieved by our epidemic routing protocol assisted by knowledge inference, supported by each of our trajectory update strategies. And impressively, across the board, our knowledge inference approach eliminates 96% of the redundant transmissions, and it does so at a small penalty. We also measured false positives, which indicate a message that was incorrectly eliminated. So next, we flipped our parameters. We fixed our p-sub propagation parameter and varied confidence threshold. And you can see this chart is kind of divided into two. After a certain point, it appears that the false positive rate almost completely disappears. It's still there, but you can hardly see it. And this happens precisely when the confidence threshold exceeds our p-sub propagation parameter. And we saw this with all combinations of these two parameters. So the takeaway here is that given I'm a developer and know something about this p-sub propagation parameter, it can help me, from an engineering perspective, choose an appropriate confidence threshold to eliminate redundancies without too much of a penalty.
Your graphs are undirected, I presume, or
Correct.
directed?
They're undirected.
Undirected. So if I learn something from you, there's no point telling you again.
Correct.
And then if somebody is neighbor for both of us, then no point transmitting.
Exactly. I can see that you already received that.
Yeah.
Okay. So I'm going to change gears here. And so far, I've been talking about constructs and methods of sharing and using data. But now I want to look at the other side of the coin. And given that data exists all around me, distributed across many devices, I want to now search for particular data very efficiently. So like I said, there is a ton of related work here because almost every single pervasive computing application provides some novel query or access mechanism that accesses data in a very efficient way. But each of these approaches make assumptions about the network or data or the environment that don't hold within the emerging kinds of pervasive computing spaces that we're seeing. So, for example, common assumption is the network is static or data is globally accessible. Some approaches expect that generated data will eventually be consumed. And many approaches use distributed data structures and network overlays that generate high overhead when the network is very dynamic or there's lots of data being generated. So we introduce a distributed search engine that is specifically designed for the scale and density dynamics of emerging pervasive computing spaces. And we call our search engine the Gander search engine, as in take a gander. So in the dissertation, we provide a formal conceptual model, which I don't have time to go over here. But at a high level, Gander uses distributed routing protocols to sample the devices available in a user's immediate environment. And each of Gander's routing protocols provides a trade-off between the cost of executing the protocol and the quality with which it samples the devices in a user's environment in terms of how well it covers those devices and also how far the query is distributed. So Gander is designed to search real-world data, which is inherently, as I've said again and again, spatiotemporal. It is inherently parameterized by both space and time. So we were curious, how do correlations in space and time affect the performance of Gander's distributed search mechanisms? So let me give you the setup here. We evaluated Gander in a simulated environment of mobile nodes that move around an environment and collect data and periodically issue queries on their environment using one of Gander's distributed routing protocols. To get a better idea of how spatial correlations impact Gander, we use a data generation tool that basically gives us one knob and allows us to change the correlations in generated data. And to explore the impact of temporal correlations, we modulate this generated data with time-varying noise. So we can turn up how temporally volatile data is. Now, to judge the quality of Gander's performance, we borrow two metrics from information retrieval, and they both compare a Gander result set to an ideal result set. The first is called discounted cumulative gain. It's called DCG, and it's a weighted ranking metric, and it basically tells me how many relevant results I have and how good they are. The second metric is a completeness metric, and just tells us, in a binary sense, how many of the relevant results did I actually obtain. So we first use our spatial correlation tool to vary the spatial correlations in data. And what these charts show is DCG on the left, completeness on the right, and the performance of each of Gander's routing protocols as we turn up the spatial correlation of data. As you might expect, in general, each of the routing protocols performs better as spatial correlation gets very high, with a couple of exceptions. Both the flooding and the probabilistic routing protocols see a drop in DCG at very high spatial correlations. And this is because more data is relevant, so it's just harder to obtain the most relevant results. Flooding, however, its completeness stays the same, meaning it obtained the same number of results, but they weren't the most relevant, just because there's more relevant data around the query issuer. Probabilistic protocol actually sees a drop in completeness, so it actually acquired fewer results in general. And this is because the probabilistic protocol exerts more effort close to a user. So because there was more relevant information, it just wasn't able to get a good sampling of the user surrounding. So we next fix spatial correlations and vary temporal correlations in data. And again, we have DCG on the left, completeness on the right. But what these charts show is that, well, as we turn up the temporal volatility of data, so as data becomes more noisy, Gander's routing protocols in general perform worse because they're not able to grab relevant data before it changes. With one little exception, the probabilistic routing protocol actually sees a bump in completeness when data is very noisy. And this is again because the probabilistic routing protocol exerts more effort and less time close to a user. So it's able to get results with lower latency before they change. Okay, let me sum up the second section, and then we'll move on to the third. So we first introduced a middleware that enables developers to program with the kinds of rules that we saw in the first part of the talk. We next looked at methods for leveraging locally available contextual history to make inference-based decisions. Next, we introduced the Gander search engine and conducted an assessment of the impact of correlations in space and time on Gander's distributed routing protocols. All right, bear with me here. Third and final piece is all about system support. So providing the support necessary to, yes, question please.
So the rules you have only apply to the data, local data, or you can do aggregation too. You can say this condition is triggered if the average goes up, or can you do that? Or?
You could do that. I didn't play around with that at all.
I see.
But you could write a rule that says, send me the results about this kind of data or its value and route it back to a sink, for example. And so you could transmit that rule in a message through the network.
And then keep collecting it.
Mm-hmm.
And maybe before you continue, one other question. I noticed that you compared these, or the comparison you showed us was mainly on fidelity, but you didn't compare in terms of communication overhead. So you had a collection of routing strategies.
Mm-hmm.
Can you comment about which one was, or which ones are more efficient, require less communication?
Yeah, so we did actually do overhead assessments in simulation. So we had a simulated Disney World environment, and we did some overhead analysis. And I could bring up those slides if you'd like.
Maybe
Okay, maybe afterwards, but
At a high level, I mean, you have
at a high level, yeah.
you have 4 different routing algorithms, and you clearly believe that they're all important. Otherwise, you wouldn't have shown us all 4.
Let me go back to this picture here just because it's helpful. So yeah, flooding we saw had the highest overhead, but sampled. It provided the best quality in terms of how well it's sampled. Whereas the random protocol, less overhead because it says always forward, but send back with some probabilistic measure. Provided a decent sampling, but better overhead. And then we also developed this greedy gossip that would kind of accelerate its probability of forwarding as it found better data. And that one actually,
Was supposed to give much better quality.
in these metrics, actually performed not well, but in terms of DCG and completeness, did really well, and at a pretty low overhead too.
Okay.
Let me jump through here. Imagine me talking really, really fast. Okay, so this third and final piece of the talk is all about providing the system support necessary to deploy our approaches in real-world environments on real-world devices. So the core of this part of the talk is a piece of mobile middleware that provides the Gander search engine to applications and users, and we use it to conduct a user study on the UT Austin campus. But first we need support for actually sending and receiving data in a device-to-device fashion. So there are actually applications today that you can go and download that need access and facilitate access to digital resources that are around you. You may have heard about FireChat, which got quite a bit of publicity last November because it was used by protesters in Hong Kong to coordinate and chat completely off the grid. FireChat uses smartphones' Bluetooth interfaces to construct large-scale mesh networks and support chat completely internet-free. It's pretty impressive. So these kinds of applications are certainly useful and pretty cool, but they require come on in. Developing these kinds of applications requires specialized knowledge of a particular device-to-device wireless protocol or native networking libraries. So it can be kind of hard to get started writing these applications. Wouldn't it be nice if there was some piece of middleware that would completely hide the complexities of actually sending and receiving data over these particular D2D interfaces? So we do just this. We created a piece of middleware that makes it much simpler to send and receive data over particular D2D interfaces. And it can either be deployed in a standalone mode, or it can be integrated within an existing application. And to provide the application-facing interface of our middleware, we use our rule-based middleware from the previous part of the talk. So rather than sending and receiving chunks of bytes over a particular interface, we allow developers to write rules that say, hey, here's a piece of data, I want you to send it at this time and location. Or I can say I want to be notified whenever this kind of data arrives. So our middleware is comprised of 2 independent services. And the first one deals with what data is shared, and the second deals with how data is shared. And we only require that developers provide adapters that define or tell our middleware how to translate between application data and serialized bytes, and how to send those bytes over a particular device-to-device interface. As a case study, we created our own hyper-localized application called Blinky. And Blinky is very much a, yes?
Middleware is currently focused on Java, meaning it's meant for Android devices.
Yes, this is specific to Android. So Blinky is very much a Twitter, but whereas Twitter is for the internet, Blinky is for your immediate surroundings. So whoever happens to be around you. And to actually send and receive data in a device-to-device fashion, we use a technique called beacon stuffing, which piggybacks application data on top of outgoing 802.11 Wi-Fi beacon packets. And the application is rather simple. It allows you to send and receive short picture and text messages. But what's special is that when I'm writing a message, I can configure the spatiotemporal propagation properties of my message. So for example, I can say, I only want this message to be retransmitted within 500 feet of me for the next 10 minutes. And these parameters map directly to a rule, which is transmitted alongside the message. So essentially, what a user is doing when they configure these settings is parameterizing a routing protocol specific to this message on the fly. Now, hardware and software support for device-to-device interaction may not be available on every single device in an application, but there may be dedicated resources that can facilitate device-to-device interactions over a particular network. An example of this is cloudlets, otherwise known as fog computing nowadays. And a cloudlet is basically just a computing resource that's connected to the internet and makes itself available to nearby mobile clients. And a cloudlet is very similar to the cloud in that it hosts services that perform the heavy lifting required by nearby mobile applications. However, unlike the cloud, cloudlets are physically and logically near the services that the clients that they support. And this provides some nice advantages, mainly very crisp client-server interaction, and it keeps data close to where it originates. Using this whole idea of cloudlets, we developed a distributed hyper-localized resource discovery service that enables nearby devices to discover one another and then interact over a secure network in a peer-to-peer fashion. So our service is designed to be deployed across many cloudlet instances where each cloudlet provides a service for a well-defined region of space. And a problem that we encountered was that, you might imagine, when a client makes a request for nearby resources, that request might extend beyond the boundaries of a single cloudlet. So our service provides some deployment parameters that enable adjacent cloudlets to synchronize resources that are close to these borders. So we benchmarked our service in simulation using real-world data sets and compared it to a centralized cloud-based approach. And what we found was that our distributed service was able to support nearby resource discovery at a pretty low penalty. And it did so with a moderate cost savings over a cloud-based approach in terms of the amount of bandwidth required per time unit. So these results themselves weren't super impressive. However, they did back up previous proof of work research done on cloudlets. So immediately you can imagine that our cloudlet service could provide ground level support for for location-based services that target very densely populated environments. Think ACL. You can imagine, wouldn't it be nice if there were like some cloudlets deployed so that we can run hyper-localized applications like Blinky in very dense environments like this. For our purposes though, our cloudlet service can be used to construct virtual ad hoc networks. So our devices can discover that we're nearby and then interact over the internet in a peer-to-peer fashion. Okay. So these first two software components provided support for physical and virtual device-to-device interaction. And we use these to create the Gander mobile middleware, which uses these to run Gander's distributed routing protocols over the internet. And then we use this middleware to conduct a real-world user study on the UT Austin campus. So I'm going to talk about that now. So very quick high-level view of our middleware. We use our cloudlet discovery service to create virtual ad hoc networks and run Gander's distributed routing protocols. Each instance of our middleware exposes a very tiny little REST interface that enables it to send and receive queries and results over peer-to-peer connections. The middleware implements Gander's query resolution and relevance metrics and constructs for executing Gander's distributed query processing protocols. I want to focus on these two graph-based data structures, though, for a second. They are going to look very familiar. So rather than having developers create structured data by hand, the middleware enables an application to compose contextually related data. So for example, the dynamic state of a coffee shop, for example, might be defined by the ambient noise level and the length of the queue to place an order or the number of available seats. So our middleware enables a developer to pre-configure these contextually related data values. And all I have to do is update them individually. And whenever I update a data value, the middleware takes care of the generation and composition and storage of the structured data item.
That's a data flow graph, those green things.
Yes.
So each of the circle is an operator.
Oh no, sorry. This is not a data flow graph. That is each of those dots represents a data value, and then an arrow represents a contextual relationship. So maybe like this top one is coffee shop, and then this is sound level, and this is available seats.
So when you update a node, how do you update the neighbor? Do you update the neighbors?
Yeah, the update propagates upwards in the tree. Okay, so we use this middleware to create a mobile application called the MyGander mobile app, and it uses input from sensors and human users to resolve queries like, which of my classmates is nearby? How long is the line at the coffee shop? And are there enough available seats in a quiet part of the study lounge for my homework group? So we instrumented a couple smart spaces in the engineering sciences building when it was around, and deployed MyGander for 15 weeks on the UT Austin campus. And for 2 of those weeks, we conducted a focus user study because we had done all of this evaluation and benchmarking of Gander in simulation. Those results are in the dissertation. But we were curious, what does it matter to the user? What is the user perceived quality of Gander's search mechanisms? Does it even make a difference? And so for the duration of our 2-week focus user study, periodically the application would prompt users to rate their search results in terms of their utility, whether or not the user was confident in the results, and how satisfied they were with results. And we averaged users' responses using 2 scales, a graded and a binary scale, and we'll see how these differ in a second here. And overall, we found that users were kind of lukewarm about Gander, which is disappointing, but there were a few interesting anomalies here. In particular, users were significantly more confident about the results obtained by the random routing protocol. To figure out why, we had to dig a little bit deeper. So we also measured how long users spent looking at their search results. And interestingly, the random protocol, users spent the longest time looking at their results that were obtained by the random routing protocol. And random also achieved the highest DCG, so it obtained the highest number of relevant results. So our conclusion was, oh, users are more confident when they're given more results. But we needed something to back this up. So interestingly, the flooding routing protocol, the user feedback for those results exhibited the highest disparity between the graded and binary averaging scales, meaning that users were middle of the road about those results. They're, whatever, doesn't really matter. So flooding also achieved the highest, or I'm sorry, the lowest DCG, and users spent the least amount of time looking at those results. So users were more lukewarm when given fewer results, and their opinions became more ossified when they were given more results. So this kind of makes sense because when I'm given more results, it allows me to make my own judgments about whatever information I'm looking for.
I'm sorry, what are the results about?
So
What are the queries and results about?
yeah, so the kinds of queries that you could issue, the data was sensor data about noise level, number of available seats in the space, and people could also input their class schedule and what they were working on. And so I could pose queries like, which of my classmates are near me and working on this homework assignment, or how loud is the study space?
So it is surprising. You would think that the flooding would get more results.
You would think that.
Yeah. So why I'm still not clear.
So
why
this is
flooding-
maybe mislabeled. This might be better labeled best effort flooding, because the flooding routing protocol generated enough traffic to crash the application on many occasions.
So people were unhappy because of that then.
Yes.
Got few results because it.
Yeah, because it crashed, yeah.
So the takeaway here is don't use flooding, basically, even in a small deployment.
Or don't crash the application. So do flooding in a smart
Okay, well,
way
yeah,
so
that
that,
too.
yeah.
Okay, so let me wrap up this third and final section. We first introduced a middleware to simplify the development of applications that need to send and receive data in a device-to-device fashion, and then also introduced a cloudlet-based resource discovery service that we use to execute Gander queries over an internet connection. We use our middleware to conduct a user study on the UT Austin campus and evaluate the user-perceived utility of the Gander search engine. Before I conclude, I want to talk about a couple of research directions that are directly enabled by this dissertation I think are pretty interesting. So in my dissertation, we focus almost entirely on distributed applications of our spatiotemporal metadata. But you can imagine if we could somehow efficiently aggregate all of the contextual history of data in a large system, that it could be mined for patterns and regularities, which could be pretty useful input to cellular network operators to, for example, trigger collaborative behavior or preload data to a particular place. I also think there's a lot more potential for designing distributed algorithms for dynamic networks. And finally, at the intersection of Gander and our spatiotemporal metadata, I think there is a ton of potential for designing contextually sensitive query processing mechanisms that are able to adapt their behavior as they find new data and that has different contextual histories. So as mobile users' physical spaces become increasingly digitally accessible, applications will require high-quality support for resolving users' hyper-localized information needs. To that end, this dissertation represents a significant step in the evolution of device-to-device systems and paves the way for, I think, some new and exciting research areas. So that's it. Thank you very much. Questions from the audience?
It's your turn. I'm not gonna do it. No? Nothing really? All right, well then take some cookies and thanks for coming, man.
Yeah, thank you for coming, everybody.
Who's buying minutes later? I think it's Evan. Sure it's Evan.
Hey, you guys, please help yourself to the food on the way out.
Good job, Jonas.
Thanks, you guys. Thanks for coming.
So the YouTube would be.
And I'm going to shut down.
We're all
Yeah,
very
okay.
sensitive.
I'm going to shut down the broadcast right now.
Do you guys have a place to hang out for you?
We work out the lab.
Yeah, or the lounge or something too. Do you
Yeah,
have
is
the
the
lounge?
lab's going to be locked.
Okay. Sort of it.
But just,
The-
6th floor.
Oh yeah, actually, just right here, the faculty lounge will be unlocked, and it's actually very lovely. There's couches and chairs.
Okay, cool.
Just right then.
all right, I'm going to shut down the broadcast now. Thank you, everybody, for tuning in. Bye.